looking at this this differential form, how many of you guys are planning on going into engineering or science, like physics or, well, mostly engineering? If you're going into engineering, I wholeheartedly recommend that you take PDEs, partial differential equations. ODEs was an okay class. Ordinary differential equations. Some schools call it DPQs. That class was okay. I felt whatever about ODEs. Maybe because I had personal stuff in my life that really tinged that class negatively, but it was okay. You will see this in your ODE class if you are going into engineering. I really recommend you take it. If you go into electrical engineering, you're going to have to take it because electrical engineering is predominantly calculus anyways and predominantly differential equations. Yeah, you're going to do a lot of differential equations, man. If you do electrical engineering, most of the things you're going to do are Fourier transforms and solving differential equations. A lot. Yeah, you might as well. I automatically got a math minor for physics, so.
My sister took one extra class and she got a math minor.
Yeah.
Doing nothing.
And I don't even regret it. I highly recommend you do it. Math is fantastic. If you get a chance to do it, take partial differential equations. It's a great class. Take linear algebra. It's a great class. I had a lot of fun with them. It's a class of matrices and spaces. That's really what it is. It was a great class. I loved it. It was probably one of my favorite math classes. I don't remember anything about it anymore because whatever, but it was a great class. But no, linear algebra you don't, but differentials you do because you will change a lot of the systems that you see in electrical engineering into differentials. So a resistor behaves one way in regular space, but if you transform that, it'll behave like a differential in a different space. And it's much easier to solve a very complex circuit differentially than it is algebraically sometimes. So you'll just do a lot of them. Anyway, so the point is, this is the differential, and if you take a look at this guy, especially you two, since I already had the argument with these three, this makes a very strong statement. What function can I take the derivative of twice and get itself? E to the x is definitely one of them. That is very true. And if you take ODEs or PDEs, e to the x is one of the solutions that you have to check. And a linear combination of e to the x's is a valid solution to this. But a linear combination of e to the x's is sine and cosine.
That's what I was going to say, but that's not.
Yeah, that's what I thought.
Aha, but then, well, if I take this plus omega squared and move it to the other side, I get a negative. So it does work out. It definitely does work out. So this is how we can kind of solve this differential equation without actually having to solve this differential equation. Is that tangerine? Oh no, never mind. I thought that was something else. I might as well just pop this open already. So this is how we ended up with. Why is this not moving? Move. Okay. This is how we end up with this first function for position. Now that's in linear space. You can see that with x's, right? But I could also translate that into angular space by replacing x with theta. And you'll see why I would like to do that in a second. To be fair, it could be sine or it could be cosine. They both satisfy that condition. And I would pick whether or not the function is sine or cosine, depending on the initial conditions. So if my oscillator starts at 0, then what is it? Not you guys. Sine. If it starts at 1 or at the amplitude, then it would. A is amplitude. A is the distance away that it starts at from its equilibrium position. So this is what they look like graphically. We did talk a little bit before about Well, we used the mass on a spring horizontally to take a look at the forces, the amplitudes, the accelerations, the energies, and the velocities at different states of the system. But we can do the same thing for a vertical mass on a spring, and we can do the same thing for a mass, a pendulum. We can do the same thing. And one of the conclusions that we came to is that displacement and acceleration are always maximum at the same time, but they're pointing in opposite directions. And that makes perfect sense if you think about what a harmonic oscillator wants to do. What is it?
So the graphs are always opposite?
What does a harmonic oscillator want to do? It wants to go back to equilibrium. So if I am really, really far to the right, the force wants to bring me back to the left. That's why they're always in opposite directions. Okay, so we had a couple new definitions, a new word, frequency, which was the amount of what? The amount of cycles that my oscillator does per second. A cycle is one complete motion per second. It's the amount of forwards and back per second, but you can also think about it as how many oscillations. You could also define it as the amount of oscillations per period because they have a reciprocal relation. You can define it both ways. Unit-wise, it's per second. It's the same. It means the same thing. Literally, it's the same thing. Yeah, because period is time.
As opposed to per minute or per hour, whatever it is.
Though the period should be in seconds, because it's the SI unit. That is the SI unit. And there are a bunch of different ways that we can define the position function. We remember that omega is angular position. So this argument in here inside of sine should always be an angle. It always has to be an angle.
We're talking about strings, right?
We're talking about any harmonic oscillator. So this could be we've only got two. We've got the mass on a spring, whether that's horizontal or vertical, and the simple pendulum. Those are the two. And they both...
Only the pendulum would have the omega.
No, both of them can, because we know that omega t is theta. From rotational kinematics, theta, angular position, is defined as angular velocity times time, right?
Yeah, but isn't a string only x
Or only y.
So?
Then how does it go rotation?
It's taking forever. Oh.
Because if you're going, springs stay in the x or the y, one or the other, so wouldn't the angle just be 0?
Yeah.
Wow. Okay, that sucks. Wow. Yeah, this is... Okay, do they have a second one? No, they have a pendulum.
Yeah, I got pendulum, it's circular.
They have that one. They have that one. The answer, if I look at a... Maybe I could just take a look at the picture. You know what? I will trust in your ability to imagine. Can we do that? Okay. So if I take a look and I were to graph the position of where this oscillator is in time as it goes up and down, what it's going to do is perfectly match the position of this particle as it cycles round and round. It turns out that a simple harmonic system is exactly the same graphically as a uniform circular motion system, as a circular system. They actually graph to be the same. Maybe this one will work. Maybe this one will work, but I don't think this one actually graphs. This one does not graph. This one shows me energy, but it does not graph. Oh, well, that's not what I want. The one that I want is this one, and the school won't let me open it. Will it let me open this one? No, won't let me open any of them. Will it let me open this one? Okay, I have to download a particular... I'll figure out a way to show you guys what this means. That wasn't the point of today, but I'll figure out a way to show you guys, and maybe I can make a video on my computer and then bring it in where it actually works. I thought this was running Windows 7. It actually is not running Windows 7. This is running Windows NT. Yeah, didn't know that. Yeah, exactly. It's exactly my point. It's exactly my point. Anyways, so the equations for simple harmonic motion actually do come from the equations for uniform circular motion. If I graph the positions of a oscillator, it doesn't matter if it's a pendulum or if it is a mass on a spring. If I look at its position, if this is a vertical spring, whatever, up and down, it'll actually match the circular motion up and down.
So it seems like there are a lot of equations. Which ones are we given on the equation sheet?
I believe you're given all of the rotational kinematic equations. You're given a bunch of area equations. You're given a bunch of interesting calculus equations. You're given the very easy dot product and calculus, dot product and cross product algebra equations. They don't actually, I guess they don't expect you to do the calculus for both of those. You are given...
I think you're given the Albert. Yeah, they're right there.
You're given the periods. You're given the period equations, and you're given the relationship between frequency and period. You're also given a version of this sine-cosine equation. They gave you the cosine version. Remember that this phi term represents, you guys remember what we talked about before?
Phi is the angle between the two vectors.
Well, okay, yeah, that was for work. That phi actually represents, oh, we're not there yet. Okay, well, let's get there. Let's actually get to that point right now. I'll show you, I want to give you that demonstration so bad. Okay, I'll figure it out. I'll figure out how to get that thing to work on this 1999 computer. Public schools have more up-to-date computers. If we take a look at the state of the energy of this system without any type of friction, which obviously means that it's not real, right? If we take a look at the case of either the vertical oscillator, the vertical mass on a spring up and down, or the pendulum swinging, what is the source of friction? Or this new word dampening, which really just means friction. Dampening means a way of slowing it down.
Damping or damping?
Damping is the same. It's the same thing.
But do they say it like that in the test?
No, it's damping, but like dampening, it's the same.
No, but do they say damping is
Yes.
like friction?
For this, yes. For the vertical oscillator and the pendulum, what is the source of friction? Air resistance is one of them. Air resistance is definitely one of them. No, because gravity is conservative. Gravity is conservative. Remember, friction has to be a source, or I'm sorry, friction is a non-conservative force. So it takes away and does not give back.
Are we assuming that the spring or the rope or whatever it's hanging on has no friction whatsoever?
That would be the second place.
Oh, yeah.
What?
So air resistance would be one of them, and that would be the most obvious place. But for the case of the pendulum, at the contact point at the top, there could be friction there. That's a really, really big place. Well, when the pendulum swings, right? Well, it's swinging on something. It's hanging on something. So there's friction up there. That's one place. For the mass on a spring, there could be friction loss either on the spring itself as it comes in and out, or it could be rubbing on something up on top. So those are really important places to think about. But if there is no friction, it's completely idealized, then the energy kind of looks like this. And that might not be super obvious as to why this is the case. Why is it this shape? Specifically, let's start with the easier one. This green line represents kinetic. That might make it easier for you to figure out why. Anybody know what shape that is? Yeah. Yeah. I would imagine it's probably, yeah, okay, sinusoidal, close enough. I think of it more as a bunch of parabolas, is really what I think of it. But why does it look like that? Why isn't it a bunch of straight lines?
Because it goes, kinetic energy as it moves in is increasing.
That's true.
And then when it's all like increasing to decreasing, but it's not like abrupt changes. It's like
No, I definitely agree with the fact that kinetic energy starts at 0
right.
and potential energy starts at max. But this is only true if my system starts where? At an amplitude. Okay, that makes sense. If my system starts at an amplitude, that makes perfect sense. My question is, why doesn't it look like this? Why doesn't it look...
As it gets farther away, it gets more resistance.
The acceleration isn't constant. Like this.
That's a very valid argument. The acceleration is not constant. What is a kinetic energy versus time graph? What is it really?
Velocity.
It is a fancy type of velocity versus time graph. Fancy. And it's actually not even a velocity versus time graph. It is a velocity squared versus time graph. That's really what that is. A kinetic energy graph is a velocity squared versus time graph. That's why it's curvy, because of that velocity squared part. Then, now that I know...
I look at it, that's the endpoint.
Well, I mean, parabolas, if I take a parabola, for example, and I zoom in at one point, doesn't it look pretty straight?
Yeah, that's what I'm saying.
That's my point. But now that I know that that the kinetic energy part needs to be at least curvy-ish, what does that tell me about the potential part? It has to mirror it. It has to mirror it because of conservation of energy. And this isn't only true for simple harmonic motion. This is true for anything. So if I had a system, let's say I throw a ball up in the air straight up, its graph would look something kind of like that. It might not repeat over and over again. It might stop at some point. But it will look something like that. The kinetic energy will be kind of curvy because that kinetic energy is squared. Even though the potential energy is not squared, it has to match the kinetic energy. It needs to gain or lose at the same rate because conservation of energy says that they have to match up. It's kind of stuck at going at kinetic energy's rate or at its pace. Now, this is only true if there is absolutely no dampening, if there is no friction. But that's not true in real life. That actually isn't even going to be true on our exam. There could be friction. There could be dampening. And that has a very characteristic shape. The damped harmonic oscillator still kind of looks like an oscillator. It still kind of repeats, but what you'll notice is that those repetitions get smaller and smaller and smaller. Kind of like you take a basketball, you hold it up at a height, and you let it go. You're going to notice that after every successive bounce, it gets lower and lower and lower. There, why does that happen? Why? That is true. But why do I know that is true, though?
Because it ends up, doesn't move at some point.
Okay. Okay, then I guess my question, you're technically correct. My question was not great. What topic? No, that's not even great either. Because it's an elastic collision that is not perfectly elastic, right? That is how I know that the energy gets smaller and smaller for sure. I can definitely tell that because the heights get lower, but I could have known that before dropping the balls by knowing that it wasn't going to be perfectly elastic. That is true. Now you'll notice that it still, number one, has a very characteristic shape, and it follows what's called an envelope. It follows this harmonic envelope that only kind of happens if the dampening is decently small. And we're going to see, or we can see, 3 cases of dampening. Can I keep going? Okay, the editing here is weird. Okay, that's not what it looks like that's not what it looked like on my end before. Now, if the dampening gets bigger, it kind of stops looking like a harmonic oscillator, and it stops having that very characteristic envelope where it has that maximum amplitude. And we'll see 3 major cases. If I am underdamped, then what I'm going to see is that I'll get a couple of pretty characteristic oscillations, some very small oscillations, but then the oscillator is just going to die. It won't uniformly go down and follow this envelope. Bless you. That's A. That's A. Bless you. So that's very, 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 very little friction, and I'm going to get away with, a couple oscillations. Granted, this is a very, very, very hyperbolized example, but I'll get away with a couple oscillations and then go away. If I am critically damped, that would be the absolute quickest way to get to equilibrium. That's the best. I don't want to use the word critical anymore. That's why it's called critically damped. That's the most efficient way of getting my system to stop vibrating. So that's when I will go from equilibrium, and I will instantly go. No, I'm sorry, amplitude, and I will instantly go to equilibrium. I won't actually start cycling up and down. I'm just going to go smoothly into equilibrium. The last one is if I'm over-damped, and in that case, I will end up taking so much time to go down into equilibrium. It's very inefficient. That's about it.
Equilibrium in this case, what is it?
That 0 point. That 0 point where my system wants to be. So if you think about this, where is the most common example you guys have of oscillators? Anybody know?
Grandpa.
Yeah, that's true, but not everybody has a grandfather clock. I think everybody in this room has the example I'm thinking of.
The fan.
Oh, no. Your car. Your car, specifically the springs in your car, are oscillators. The ones in your suspension, they are oscillators. And when you get in your car and you sit down and you go up and down, what do you normally feel your car do? It tends to rock, right? Depending on how many of you guys have really fancy cars that have like different suspension settings, like race mode and touring mode and sport mode? Yeah. So what that does in your car, especially if you have something like a BMW or a Mercedes, like one of those high-end ones, they use magnetic suspensions where they've got ferrofluid in the magnetic, so that they run a magnetic field through it and it changes the density of the fluid. Whatever, it doesn't matter. The point is that it changes the dampening of the springs so that it can go from a system that might be underdamped, because maybe you want the car to absorb a little bit, to kind of jiggle a little bit. That might be something desirable. For example, if you're in a family car and the goal that you want is comfort. You want the car to vibrate, or actually the frame of the car to vibrate, so that the body of the car does not. So that the people that are sitting inside of the car are nice and comfortable and they don't feel all those bumps in the road. So this is the thing that you're trying to get. So maybe your car has a comfort setting, and it goes to that. That's where it goes.
I don't understand overdamping. How does that mean?
Overdamping means that it is real.
Holy, guys, I'm scared of fire drill.
Well then.
I swear, I'm not